All right, next slide. So a sequence was a list of numbers. And we use a couple of different notations for sequences. You might see a list like this. You might equivalently see something like this, where there's some function inside of closed brackets. And we say what numbers the index runs through. This is sort of like summation notation. It's supposed to be an infinity. You also might see it written in the form of something like an is equal to f of n. So as an example here, the sequence 1/2, 1/4, 1/8, 1/16, and so on, assuming the pattern continues, could equivalently be written as the sequence 1/2 to the n, where n runs from 1 to infinity, or it could be written in this form an is equal to 1/2 to the n. And we consider all of those to sort of be equivalent to each other. And yet there's a little bit of ambiguity in this one, because I might be referring to the specific term an, or I might tell you that the sequence is generated by that function. Okay. In any case, the idea here is that each term of the sequence is gotten by taking that index in and plugging it into the formula. So 1/2 squared, which is 1/4. This is called an explicit formula. You tell me the precise formula. You tell me which term you want. I've got a formula. I plug the number in. I get the term. Okay. All right. Now, the reason that we want to do that, or I shouldn't say not the reason we want to do that. So now the fun direction of this, and one that students often don't like, especially if you've seen this before, is if I ask you to do this in the other direction, where I give you a pattern and tell you to find the formula. I happen to find these highly amusing, but I ended up doing a PhD in math. So that whatever that says about my taste in fun things to do, I'll leave you to your judgment here. But like as an example, I might say go the other direction. Given a sequence 3/5, 4/25, 5 1/25, 6 6/25, find a formula for an. Right. I like these. They can be rather challenging. So the basic game, when you see a problem like this, is it's a pattern recognition game. And part of the reason that this is hard is because there's no specific technique that I can tell you to do. You have to look at this and try to figure out what the pattern is. The easiest way to get started is to write down the terms that go along, the indices that go along with each term. So this is the n equals 1 term. This is n equals 2, n equals 3, n equals 4. And then see on the basis of the index how you can reconstruct the pattern that gave rise to that. It's not so hard to see that in the numerators here, that 3 is equal to 1 plus 2, where that's the index. And 4 is 2 plus 2, where there's the index n right there. And this is 3 plus 2. And this is 4 plus 2. So I'm going to guess that there's probably an n plus 2 in the numerator of this pattern. Okay. Because the idea of these formulas is to relate the index to whatever you're seeing happen in the terms. This example is pretty easy to see what's going on here. What's going on what's going on in the denominators?
The terms are squared.
So almost, I mean, so 25 squared is not 125, it's 625. So what happens between here and here?
It's
multiplied by 5.
Multiplied by 5. Okay, so is there a way I can keep track of multiplying by 5 as I increase the index? Because I have to relate this. Okay, so yeah, so from Valeria, 5 to the n, right? So 5 to the n is, so one way of looking at this is 5 is 5 to the first, and 25 is 5 to the second, and 125 is 5 to the third, and 625 is 5 to the fourth. And again, we can see that these powers track along with the index, right? In fact, we don't have to adjust them. They just are the index. Now, this is not a proof that this pattern evolves from an is equal to n plus 2 over 5 to the n, but we don't need that. Proving these things is the subject of a different course, right? So if I ask you to find a formula, you always get to make the assumption the pattern continues, and you just look and eyeball it, right? Assume the pattern continues, don't prove it, just write down a formula. Maybe in a previous class, you guys have proved these things with induction. We're not doing that. Okay, so is it the case that every sequence has a as a formula? And of course, the answer is no, right? So famously, if you look at this sequence, so this is called the Fibonacci sequence. And this sequence is generated recursively. So what I mean by that is you get the previous terms by adding together pieces of the previous parts of the sequence. So 2 is 1. So you do 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8, and so on. So if you were going to write a formula down for this one, you have to say, well, the first term was 1, and the second term was also 1. And once I know the first two, I can find all the rest of them by just turning the crank. Fn is equal to Fn minus 1 plus Fn minus 2, where this sequence is called recursive. This is a recursive sequence as opposed to an explicit sequence, because if I say to you, find me the thousandth Fibonacci number, you have nowhere to plug a formula in. You actually have to calculate 999 previous Fibonacci numbers to get the 1000th one. Okay. And this does not have an easy explicit sequence. So this does not have an easy explicit formula. In fact, if you're interested, I think it's something like Fn is equal to 1 over the square root of 5 times 1 plus root 5 over 2 to the n minus 1 minus root 5 over 2 to the n. How's that for an, yeah. You're not just going to stumble across that. So there's whole methods that you use. I mean, there is a method for doing this. It's pretty easy to walk through. If anybody's interested, I'd be happy to show you how to do it. But again, outside the scope of what we're going to do here. But the idea is, just because you have a sequence does not mean it's necessarily going to be easy or even possible to write down an explicit formula for it. Okay. All right. So just like functions, sequences can have limits. And what we mean by that is we say a sequence has a limit if it gets arbitrarily close to some number. And by arbitrarily close, I mean at some point, every term in the sequence is close to whatever its limit is. It's identical, actually, to the definition of a limit for a function. So we say that the limit as n goes to infinity of an is equal to L if for some capital number n that is far enough out in the sequence, if there's some big number n, so that for n bigger than n, I'm not going to write epsilon delta here, I promise. So that n bigger than n, an is arbitrarily close to L. Basically, this is the same as saying it has a horizontal asymptote. That's what we're after here when we talk about limits of sequences, right? So you think about a sequence as being on a graph. A sequence on a graph kind of looks like this. And if that sequence gets arbitrarily close to some number, like it was a horizontal asymptote, this is a way of drawing sequences, by the way. You can just put the n axis and the f of n axis, and you can just plot them as a sequence of dots. And if that sequence of dots has a horizontal asymptote, then the sequence has a limit. If that limit exists, we call the sequence convergent. If the limit as n goes to infinity of an exists, then an is called a convergent sequence. I apologize if I'm going too fast. I'll take some feedback after the class. You guys can tell me if you want me to speed up or slow down. I will post these so that you can go back and watch this again. Okay. If not, an is a divergent sequence. And then there's this weird borderline case where sequences can be said to converge to infinity. Right? So to converge to infinity means the sequence gets arbitrarily large. Everything in the sequence gets arbitrarily large. You draw me some line, this whole sequence is above that line forever at some point. Right? So there's this borderline case where to converge to infinity means if you draw me any line m at some number m, then eventually, no matter what the sequence does down here, if eventually it goes over that line and stays over it forever, no matter what m you draw, then it's possible that we could say the limit as n goes to infinity of an is infinity. And Stewart kind of goes back and forth about whether converging to infinity means convergent or divergent. He flops around, right? When you guys learn limits in the limit chapter, he told you the limit exists and also it's equal to infinity, which means it diverges. So infinity is kind of a strange animal here. With sequences, we do often talk about converging to infinity. I probably will go with Stewart and Webassign, and I believe Webassign says that the limit being infinity means it's a divergent sequence. So just go with whatever the Webassign says. I did give you 100 attempts per homework exercise, so those aren't terribly difficult to do. Okay, now the reason that we care about having limits and these explicit formulas is because as soon as you have limits, you can use all the limit rules we already know. If we think about limits of sequences, we're allowed to use all of our limit laws. Limit laws apply to sequences, even the most useful one of all because of the existence of a theorem. And so I'll note here, even L'Hopital's rule. So that means we can use standard techniques of calculus to investigate whether sequences converge or not. So let's consider this sequence. So when I look at that, I think, all right, I know how to deal with a limit that looks like that. It's not quite what we dealt with in earlier calculus class because the n here, n is an integer. So all of our fancy continuous function tricks don't really work until we notice that the book says, oh, well, it's totally okay to actually think about this. If this limit exists, it's the same as this limit. You don't actually have to make this step. I just think it's important for me to point it out, right? Where now x is a real number. And that means you can use all the calculus. You can use derivatives on it. You can use L'Hopital's rule on it. You can use the standard limit computations you guys learned way back in like chapter 2, or if you didn't do this at Poly in your high school classes. So computing this limit is the same as saying, oh, well, one of the standard moves you can make here is to write this as the limit as x goes to infinity of 1 over 1 plus 1 over x. So what I did there was I divided the top and bottom of that fraction by x. You just clear the largest power, right? This is dividing by largest power. This is like a pre-calculus idea. Divide by the largest power of x. What is left over? Well, there's a 1 over x as x goes to infinity, and that means this entire limit is just 1 because it's 1 over 1 plus 0. So this sequence converges. Okay. We could have done that with L'Hopital's rule if we wanted to as well, because remember L'Hopital's rule applies to indeterminate forms. This is an indeterminate form of infinity over infinity type. So we could use L'Hopital here. Now, show you an example of a divergent series, because you might start believing every sequence converges. So there's this guy, which is called Grandy's series, I think. So it just alternates back and forth between -1 and 1. You can think about this as a sequence an is equal to -1 to the n. Now that sequence does not necessarily look terribly badly behaved. I mean, if you drew a picture of it, goes like this. First, it has a value of -1. Then it has a value of +1. Then it has a value of -1. Then +1. Then -1. And just keeps doing that forever. The reason that the sequence diverges is that it never settles down on one number. There's not a single horizontal asymptote that this is approaching. So there's no horizontal asymptote. It just keeps flopping around for all of eternity. And that means it never settles down on a y value, right? Since it forever flops back and forth, this is a divergent sequence. Even though it's bounded, it never gets above 1 and never gets below -1, but still it is divergent. If you want a more interesting example of a divergent sequence, you could look at something like the sine of 1 over n is another one that like takes on every possible value forever. Okay. So this is a divergent sequence. Now it is a bounded, but it is bounded, which I'll define on the next slide. That means that it never goes above, there's some number, 1 in this case, where it never goes above 1 and it never goes below -1. The whole sequence is contained in some specific finite amount of y values. Okay, so bounded sequences. So an is bounded. I'm going to use a slightly different definition in the book because they talk about bounded above and bounded below, which don't matter so much in this class. But an is bounded if there is a number m so that -m is less than or equal to an, which is less than or equal to m for all n. So every single thing in the sequence is squeezed between these two values. The picture of that looks like this. You have m and you have -m. And whatever the sequence does, it can't get out of those. Okay, that's an example of a bounded sequence. So it's trapped. Now notice, bounded by the previous example, bounded does not mean convergent. So there's one other structural feature that sequences can have that actually guarantees that they converge. In fact, a lot of math is about finding the nice objects to work with. And so bounded is nice, but not nice enough to guarantee that a sequence converges. We need one more feature, which is called monotonicity or monotone. So we're going to look at sequences that are either increase forever or decrease forever. So let's talk about monotone sequences. Monotone sequences. So an is monotonic or monotone if either an is increasing. And because there's some ambiguity on this page, I'm going to use this for the sequence notation, because I'm going to be referring to specific terms. An is increasing, which means that an plus 1 is always bigger than an for all n. Each term is not strictly, is bigger than or equal to the term that came before, is what I mean by increasing. So a sequence increases is as I go down the sequence, the numbers get larger and larger. As an example here, you could think something like 1/2, 3/4, 7/8, 15/16, and so on. That's an increasing sequence because each term is larger than the term that came before it. Or an is decreasing. And that's the same as saying that an plus 1 is less than or equal to an for all n. As an example of a decreasing sequence, let's do one that could say converges to minus infinity, -1, -2, -3, -4, -5, and so on. That sequence decreases forever. Each term is strictly less than, or not strictly, each term is less than or equal to the term that comes before. And the reason that this also doesn't necessarily mean the sequence converges, right? Monotone just, I mean, it could be running away to infinity or minus infinity, and those aren't nice either necessarily. It's the combination of the two things that forces a sequence to have a horizontal asymptote. So this is one of the big idea here of like the sorts of sequences that we want to work with is called the, it's got the fancy name it's called the monotone convergence theorem. You don't need to know that. I'm just telling you that's what it's called. It's not theorem. The monotone convergence theorem says that if an is bounded and monotone, then an converges. You can think here what's going on is you've got some bound, and say the sequence is bounded above and monotonically increasing. Well, if it's going up, it has to go somewhere, right? I mean, it can't go back down again. It has to keep increasing. Well, at some point, it just runs out of places to go. It has to go up, but it can't go above that line. So that line must end up being something like a horizontal asymptote. That's the sort of idea running around in the background here. Okay. And here is possibly the most useful and in terms of later applications, and one of the more irritating things to have to be able to do, which is to show that a sequence is increasing or decreasing. So I know there's a couple of these on the homework, so let me do a quick example. You might be asked something like, show that n over n squared plus 1 is a decreasing sequence. And the way that you do that is you just work with the inequality. It's going to be decreasing if and only if an plus 1 is less than or equal to an for all n. And there's no magic here. I know like some people that have seen these things in the past, it's like you have to find the answer and then start from the some true fact and then reverse engineering it to the correct answer to the question. For the purposes of this class, if you're manipulating inequality with algebra, it is okay to say something is true if and only if the algebraic manipulation of it is also true. So I would say this will be true if and only if n plus 1 over n plus 1 squared plus 1 is less than or equal to n over n squared plus 1. There's going to be a lot of this where we take formulas and we have to plug in a different index into the formula. So notice here that I've just replaced the n's with n plus 1 because I'm taking the index of that term and putting it into the explicit formula that generates that term. So this is an plus 1 and this is an, because this is an. And then if and only if you do a bunch of algebra. And what falls out at the end of doing this algebra is you cross multiply, expand out, cancel like terms, collect stuff, and you end up with this. And that turns out to be true. This is just true for n bigger than or equal. Remember, n has to be a positive integer, and n squared plus n is always bigger than 1 if you start with 1 and you only put positive integers in. So since this is true, this was true, and since that's true, the sequence must have been a decreasing sequence. Okay, so the logic here is you start with what you want to hold, you find some true fact, and because all you did was algebra, the first true fact is true if and only if the last one is, and you can just leave it like that. All right, so I apologize for going longer than I normally will on a virtual setting. Normally I try to do about 30 minutes of math, which I believe I've done today. I'm going to, are there any questions about any of this stuff? Anything I can answer? I mean, like I said, it's pretty easy out the gate, but I'm happy to answer any questions about stuff if anybody has any. Any procedural questions, math questions? All this is going to be up on Canvas. I'll post the notes I did in here. I'll post the recording of this video. I'll post the notes for my other supplementary video, which will be up on the YouTube channel. I promise this will be more fun once we're back in person. Anything? Okay. So there's a question about Webassign. So yes, on a given, I guess I didn't clarify that. So on a given week, what I will do is I will assign a pile of Webassign assignments for what I'm going to cover. So like this week, I plan on covering 11.1, 11.2, and part of 11.3. So we're going to spend some more time with 11.2 than we did on 11.1. 11's sort of introductory. Typically, the homework will all be due, all of it, on Friday at midnight. And that gives you guys an opportunity to ask me lots of questions about what we're doing. I can adjust the homework. So if I don't cover what I want to cover, I can push stuff off into the next week. But yeah, so Fridays will be when homework is due, right? With the exception of exam weeks. I give exams on Fridays because I prefer to have them at the end of week after people have a chance to ask me questions. But so there'd be the quiz. So like this week, if we were on a regular schedule, quiz 1 would cover 11.1 and 11.2, and that's it. And then next week's quiz would cover like 11.3, 11.4, and 11.5. And so I try to align the quizzes with the homework that's due. So you're supposed to keep up with the homework and then get measured on how well you understand what's going on in the quizzes. I don't think it's going to happen this week that we're going to have a quiz, but we'll do one next week. And they're just little shorties, like 10, 15 minutes. Okay. So what I want everybody to have is this week on Friday, you're supposed to have done 11.1 and 11.2. If you don't, you can request infinite extensions. Okay. But that's like having the due dates is like giving you a guide to like, hey, keep up, because if you get blown out or you end up having to do 6 sections late or something like that, you're going to get destroyed in this class because it moves fast. And also it also has like 6 different ideas in it. Famously, this class is like a grab bag of different ideas. So you don't want to get behind. Each individual chunk is it relies on itself, but catching up in here is a bad idea. So I try to build in some forgiveness, but I'm also trying to like strongly suggest that you keep up. Anything else? All right. So I guess I will, I'm going to stay in this room because I've got another class coming up in the next period, same class. So yeah, it's I'm sorry I can't meet you guys in person. I'm looking forward to meeting you in person and doing this on a chalkboard. So if you got questions about anything on the homework, please hit me up in Slack. I'm going to try, even in this sort of virtual piece, I'm going to make this as interactive as I possibly can. So. All right, then I'm going to mute myself and kill my video here, but it was lovely having you guys. Thanks for putting up with I really appreciate putting up with the last minute change. I know it's obnoxious, and I have to imagine that's probably been pretty chaotic for everyone. So yeah, you have my Oh, that's not sympathy is not quite the word. I appreciate it. Thank you. And I will also try to extend the same appreciation or, courtesy to you as well. All right. All right. Take care. And I'll see you next week or next week. I mean, next day, Tuesday. Bye.
Thank you.
Thank you.